We're going to be talking about exponential and logistic functions.
She literally doesn't make anything better. She hates our class. Maybe I'll take notes.
I love that idea for you, Nora. So, in your Algebra 2 class last year, did you talk about exponential and logarithms? Did you do that? Okay, I'm just double checking. Some years that doesn't always get to, and it matters to me like how I'm going to approach things if it's the first time versus the second time. It's the first time every time. Okay, that's good to know. All right, so we're just going to start off by defining what we mean by an exponential function. So we say an exponential function is just something that can be written in the form of a times b to the x. We have a couple of restrictions here. A can't be 0. Why don't we allow a to be 0? What would happen if a was 0? Whole thing becomes 0. That's a constant function, not an exponential. That's why we don't allow that. We don't let b equal 1. Why can't b be? What would happen if b would be 1? What would happen if b was 1?
Oh, that would just be 1.
Yeah, 1 to the x is 1, and then 1 times a is just a. That's another constant function, right? So we don't let b equal 1, and we say that b has to be positive. What would happen if we let b be negative? This is a harder question. Why don't we want to allow for negative b's? A negative line, no, and that's not quite right. So notice where the x is in this equation. Where's the x at? In the exponent. And x can be anything, right? Any number. So what would happen if b was negative and say x was 1/2? What happens if you have an exponent of 1/2? What's that the same as?
Square root.
A square root. And what happens when you square root a negative?
Imaginary.
You get an undefined answer, an imaginary result, right? And that doesn't happen just for 1/2, but would happen for 1 over any even number. So like 1/4, 1/6, 1/8, 1/10. So you'd have something with like infinitely many undefined values. And this is starting to behave like nothing we want to deal with, right? Is everybody good with understanding why we disallowed those particular values? When we talk about an exponential function, we called this a, the initial value, and we call this b, the base for our exponential. So a key feature for all exponential functions that are of the form a times b to the x is that they all have horizontal asymptotes at y equals 0. So question for you guys. Is that true? 2 times 3 to the x is equal to 6x. Reagan, you say no. Why do you say no? But why not? Okay. You're right. You can't multiply them. When could you multiply them? So there's 2 situations when you can multiply these things. If they have the same base, how do we multiply exponentials with the same base? You add the exponents. Very good. Or if they have the same exponent, what can you do? Multiply the bases. So you can't do anything if the base is different and the exponent is different. There's no simplifying that can happen there. If the bases are the same, you can add the exponents. If the exponent is the same, you can multiply the bases. Does everybody feel okay about what's okay to do and what's not okay to do? Very important piece here. This is one of the most common errors I see made, particularly when you start talking about solving, as people start dividing both sides by 2 and like dividing the base of an exponential, and you can't do that. All right, let's do a couple of quick examples here to kind of refresh ourselves on our exponent properties. So let's say we have the function f of x equals -2 times 4 to the x. If I do f of 2, what am I going to do? What does f of 2 mean? Yes. So -2 times 4, and then in place of the x, I'm going to put a 2. All right, if I want to simplify -2 times 4 squared, what do I do first? The exponent. What's 4 squared? It's not 8. 16. And then -2 times 16 is -32. So far, so good. So if I do f of 0, again, we do the exponent first. What's 4 to the 0? It's 1. Remember that any number other than 0 to the 0 power is 1. What's 0 to the 0? Not 0. It's not 1. It's undefined. Like dividing by 0. Okay. So if I do f of -3, how do I do a negative exponent? Right, I have -2 times 4 to the -3. How do I deal with a negative exponent? Makes a reciprocal, right? It makes a reciprocal. Um, 4 to the 3rd is 64. What do I get when I multiply 2 by 1 over 64? Great. So we just reduce, right? So far, so good? So if I do f of 1/2, how do I do 4 to the 1/2? AJ, how do I do 4 to the 1/2?
Square root of 4.
Yeah. And what's the square root of 4? 2. So just making notes of these other properties. So what if I do f of 3 over 2? How do I do 4 to the 3 over 2? Well, let me give you a hint. I'm going to be using that property, the exponent of an exponent property, because 3 over 2 is really the same thing as 3 times 1/2. Everybody agree? 3 over 2 is the same as 3 times 1/2. So I'm going to use it to go that way. So I can rewrite that 4 to the 3 over 2 as 4 to the 1/2 to the third. Is everybody okay there? What's 4 to the 1/2? It's the square root of 4. What's the square root of 4? 2. What's 2 to the third? 8. And then negative 2 times 8 is negative 16. Does that feel okay there? Again, as we're doing this, if we need to refresh on any of these exponent properties, or if you ask like, hey, what's the rule for how you just did that? Like, feel free to stop me and ask, and we'll restate some of these exponent properties if you need them. Okay? Probably the second most important set of rules from algebra, well, probably the first most important set of rules from algebra 2 that you really study are these exponent properties. The single biggest skill you study is probably factoring, right? All right. Do another example here. What if I give you some x's and y's, and then I ask you to write the exponential function? So here's a table of x's and y's. I'm going to ask for you to write the exponential function. So the equation we want is going to be ab to the x. So we have to figure out an a and a b from this. Now there's two situations. One situation that's really easy and one situation that's not as easy. The easy situation is if one of the x's is 0. Because if I plug in x and y into my function, I have 3 equals a times b to the 0. Now, what is b to the 0 equal to? How do you know it's, well, could be 1. It could also be undefined, though. How do I know that b's not 0? It isn't, and there's a reason. Just asking for the reason. You're right, it is 1, but why can't b be 0? Go all the way back. We defined it that way, right? Yeah, so no, it can't be 0. So yes, 100%, that's just 1, so a is 3. Everybody feel okay there? Now I'm going to pick a second point, say this one. And I'm going to plug that in along with what I know the answer for A is. Now I can solve for B. So divide both sides by 5. So I put those two together. And I can say y equals 3 times 5 to the x. Can I say that's 15 to the x? What do you think? 15 to the x? Sound good? Don't shake your head yes at me. That's wrong. You definitely can't do that. We just went over that you can't do that. No, that's what it has to stay as. Can't simplify it. The bases are different and the exponents are different. You can't combine those two terms. I tried to trick you. I didn't. Don't be fooled by me. So that process right there, pretty simple, right? Not terribly difficult. So the natural question is, okay, Mr. Kulik, you said that was the easy situation where I was given 0 for x, right? What does it look like if I'm not given a 0 for x? That's probably the hard situation, isn't it? Well, it's the harder, sure. So let's look at this example where neither of my x's are 0. Again, I know I'm going to be writing an equation y equals a times b to the x. All right, well, I'm just going to pick one of these and plug it in. What do I have? I have an equation with 2 variables in it. I can't solve that for a number with 2 variables in there. Well, what happens if I plug the other one in? Maybe that'll be better. Nope, still have 2 variables in it. But what I have now is 2 equations with 2 variables. Hey, that can be like a system of 2 equations, right? I'm going to solve that system. You could use substitution or elimination. I'm going to do this via elimination. So I'm going to refer to this as equation A and equation B. In chapter A, where we talked about solving a system, whenever we did elimination, the variables were being added or subtracted from one another, right? So to eliminate them, I added or subtracted the equations together. Here, my variables are being multiplied together. So to do the elimination, I am going to divide the 2 equations by each other. And my rule of thumb is I'm going to pick the equation with the bigger exponent. So -1 is bigger than -3. And that'll be like the numerator of my division problem. So when I divide the left-hand sides, I get 12 divided by 48. And when I divide the right-hand sides, I get a times b to the -3 over a times b to the a times b to the -1 over a times b to the -3. So far, so good? What's 12 divided by 48 reduced to? What? 1 over 4. Good. And then what can I reduce from a times b to the -1 over a times b to the -3? You can do that, right? But how do I simplify a to the -1 over a to the -3? Does anybody remember how to do that? Yeah, that's the rule. You subtract the exponents. So what is -1 minus -3? 2, right? Now how do I solve for a? Or, I'm sorry. Why did I write a's here? How come nobody's hopping mad about me doing that? Those are obviously supposed to be b's.
Sorry.
You're fine. Ellie! How do I get rid of the squared on the b, though? Square root it. Yeah, absolutely. When I square both sides of an equation, I get plus or minus. How do I square root a fraction? Who remembers how to take the square root of a fraction? I square root the top. The square root of 1 is 1. And I square root the bottom. The square root of 4 is 2. So I have two answers to this, plus 1/2 and minus 1/2, right? Nope. Remember, what are the restrictions for B? Has to be positive. So guess what I get to do? Discard that negative. So just B is 1/2. So now that I know B, I can solve for A. I'm just going to pick one of these two equations. I'm going to pick equation B. It doesn't matter which one you pick. And I'm going to plug in my value for B. And now I'm going to solve for A. What is 1/2 to the negative 1? How do I simplify that? What does the negative exponent do? Makes A. Starts with an R. Reciprocal. What's the reciprocal of 1/2? Okay, or just 2, right? So if I divide by 2, I get A is 6. As a note, whenever I have a fraction to a power, I want to make sure that I put a parenthesis around it, because this, if I don't, this just means 1 to the x over 2 to the first, which is not the same thing as this, because this equals 1 to the x over 2 to the x, right? So really important, when you have a fraction as the base of your exponential, that you put a parenthesis around it. Everybody cool? Yes or no? You see the way I'm saying it? Why it needs to be there, how if I don't put it there, it means something different. We got to make sure we're being clear. So of all the possible numbers that we can pick, or that we can use for the base of our exponential, for that value of B, there's one number that is special. It gets a special name, it gets a special symbol. That number is called the natural base, or Euler's number. It's an irrational number, which means that you can't write it as a fraction. It's an infinite decimal that never repeats. It's like pi. In geometry, instead of writing 3.1415, yada, 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 we just use a symbol pi so we don't have to write all the decimals. We're going to do the same thing here. This special number is 2.7182818, yada, 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 on forever. Instead of writing that number, we're just going to write the letter E. Okay? We're going to write the letter E. And there's a good reason why we use this particular number, but it's beyond the scope of this class to discuss how we arrived at this number or why this number. You're just going to have to take it with a grain of salt, that this is a special exponential base. We arrived on this number for a reason as it being special. We'll talk about how we'll use it But I'm not going to get into like where the derivation comes from because it's kind of beyond the scope of what we need to be able to do. Is everybody okay? If you're curious, you can probably do some light Googling and find a decent explanation, but all right. So, that being said, what we'd eventually like to do is be able to compare one exponential with another. Specifically, we'd want to be looking at how fast is it growing relative to the other one. The most effective way of doing that is to rewrite the exponential so that they have the same base. The base that we would choose to use to do that is Euler's number, this E, 2.718, yada, yada, yada. So another way we can describe our exponential functions is writing them in the form y equals a times e to the kx. So we have this extra parameter k now. But this is just another way of writing an exponential. Now, notice that I am not talking about how to go from y equals a times b to the x to y equals e times k to the x. Not talking about how to do that. I just want you to appreciate that we can if we wanted to. We're not going to talk about how, though. Again, right now, beyond the scope of what we're trying to do. Just take my word for it that this is possible. And I can't remember exactly where we get to here, but I think we probably address it later on because we need some tools that we don't have yet. Okay. So the next thing I want to do is talk about types, what? Of exponential function. We have two types. We have growth, and then we have decay. In growth, if we're in the form y equals a times b to the x, that means that if a is positive and b is greater than 1, it's going to be exponential growth. So in the same form with a positive a, if b is between 0 and 1, it's going to be decay. If we're in this other form with the e, with a positive a, if you have a positive k value, you'll be growth. And if your k value is negative, you'll be decay. What do you think happens if we let the a be negative? Well, the criteria for the b's just flip. Or in the case of the other form, if we let a be negative, then my criteria for the k flips. Is everybody okay? So fairly easy way to just look at the equation. You can tell right away if it's growth or decay. Yes? All right. So let's look at a couple of examples. And then we can move on to logistics, I think. All right. So it says, given the population of a certain city in 1990 is 782,248 people, and the population of the same city in the year 2000 is 895,193 people. And assuming the population growth is exponential, in what year will the population reach 1 million people? So this kind of problem is a two-step problem. The first step is we have to write some equation, a times b to the x. I know I want an exponential equation because it tells me that the growth is exponential. Everybody's okay? Step 2 is I'm going to then want to solve that equation where it's equal to 1 million. Is everybody okay with the two steps? So the first step, when I read this, I want to decide which quantity should be my x and which one should be my y. Remember, the x is the independent variable and the y is the dependent variable. My two quantities in the problem is the year, the date, and then the population. Which one should be the independent variable, the date or the population? Which one is the independent variable? Date or population? Maybe let's ask which one is the dependent variable. Maybe it's easier to think about it that way. Which one depends on the other? The population depends on the date, right? Everybody agree? Okay. So when I look at this, I see a point, 1990, 782, 248. And when I look at the other piece of information, I see the point 2000, 895, 193. Everybody okay there? What do you notice, though, about the 2 points that I have? Neither one of the x coordinates is 0, right? Wouldn't I much rather have the x coordinate 0? So here's what I'm going to do. Instead of defining x as the year, I'm going to say x is the years after 1990. If I do that, what does the x coordinate become for the first point? 0, right? 1990 is 0 years after 1990. What does 2000 become? 10. And again, the reason I'm doing that is so now I have a 0 as my x-coordinate, which makes this way simpler because my a now is just like given to me. So to solve for b, I have 895,193 equals 782,248 times b to the 10th. You okay, homie? Yeah. How do I solve this for b then? What should I do next? To solve this equation for b, So you're going to want to divide by the 782. And then how do I get rid of the 10th power on there, on the b? What's going to cancel out that exponent of 10? Well, what if it was just b squared? How do I cancel out the squared? Square root. So how am I going to cancel out the 10th? 10th root. Right? No big deal. Mr. Kulik, I don't know how to do a 10th root. You just do it on your calculator. And then technically I get a plus or minus, but I know the b's are always positive, so I don't even bother really writing the plus or minuses. So if I go look at my calculator, yes sir, I type in the number 10, and then I press math and command 5. That makes a 10th root. And then I can just do my fraction command and type that in there. So my b is about 101. So taking these two together, I get y equals 782 248 times 1.01 to the x. Now, let me tell you something important about these exponential functions we're about to solve. They are extremely sensitive to rounding. So even though I wrote 1.01 on my paper, when I type this into my calculator, I want to keep all of my decimals. The easiest way to do that is I'm going to store that number into a variable. To do that on my calculator, I'm going to press this STO button right above the on button. So it's storing whatever was the last entry. And I'm going to store that into the letter B because it's the B in my equation. It seems like that makes sense to me. Okay. Now, to solve this, I have 782 248 times that 101 to the x equals 1 million. Right? Everybody good? All right. To solve this, does anybody remember what you need to do to solve this from Algebra 2 last year? What tool am I going to need to get that x out of the exponent? Does anybody remember? Great! Nobody does. So if I told you to forget what you remembered from last year, you've already accomplished it. Way to come to class prepared. So to solve this, since I don't know how to get that x out of the exponent, what I'm going to do is I'm just going to do this graphically. So I'm going to type in both sides of my equation into my calculator. Notice instead of typing 101, I'm going to use the letter B, which I stored that all the decimals to that 101 number into my calculator. So I type the left-hand side and the right-hand side into y1 and y2. And I'm going to graph this. Before I start, I'm going to choose a window, and I'm going to choose it myself. So remember, the x is representing the years since 1990. What should be the minimum x I choose here? What do you think? Lexi? I would pick a different number. The x represents the years since 1990. What x should I pick as the smallest x? 0 is a great answer. Much better than your first one. X max has to be more than what number? What number do I know the X max has to be bigger than? Well, of course, it has to be bigger than the X-min, but it also has to be bigger than 10. Because at year 10, I'm still not more than 1 million, right? So I don't know what to pick here, but I'll pick something that's bigger than 10. Maybe I'll pick 30. It doesn't really matter, but I'm going to try to pick something that's, let's make sure I get it. Now the Y's represent the population. What's the smallest population I'm concerned with? The 782,248, that's the initial population. I know if it's growing, it's never going to get smaller than that, but I'm too lazy to type all those numbers in by hand, so I'm just going to type in 700,000. Everybody's okay with that? The Y max must be bigger than what number? Of course, bigger than the 700, or the 782 even, but really what number does it also have to be bigger than? Nope. It does have to be bigger than that, but that's still not going to be big enough. Potentially not big enough. What are we solving for? When it's 1 million, right? The Y definitely has to be bigger than 1 million, or I'm not going to be able to see when it intersects. So here I'm going to do, I don't know, like 1.25 million. Okay, and then I'm hit graph. So this is my population curve. That's the function that we just wrote. There's the line for 1 million. This is the point that I'm interested in. Second, trace, intersect command, enter, enter, enter. So X is 18.2. And what's the unit for that? What is X? What is the unit for X? Years after 1990, right? Now, what does the question ask for? In what year will the population reach 1 million people? So what year, if it's the answer is 18.2 years after 1990, what year should I write here? Okay, during the year 2008, right? Probably sometime in the spring of 2008, since it's 18.2, be like within the first quarter of the year. Everybody agree? Now notice I'm going to point something out to you. The phrasing here, yes, of course. The phrasing here is going to be important. It asks in what year. In some of these questions, we'll ask you at in the beginning of what year would the population reach 1 million? What would the answer be for that? So it would be it wouldn't be till the next calendar year when the population would be over 1 million at the start. So our answer would be 2009 if it said the beginning of what year, right? So be careful with the way the question is phrased, because sometimes we're going to round up no matter the decimal or round down no matter the decimal. It just kind of depends, right? So if this was 18.7, if it asked in what year, it's still 2008. We're still not rounding that up, even though if it's, 18.99, still don't round up. It's still during 2008 that we get to 1 million. If it's the beginning of what year, even if it's 18.000001, we're rounding up to 19. Okay? All right. So the next thing we're going to talk, or type of function we're going to talk about is called a logistic function. You did not talk about this in your Algebra 2 class, so this is going to be brand new to you, or to all of us, I would suspect. We say that a logistic function is something of the form f of x equals c over 1 plus a times b to the x. Or it could be c over 1 plus a times e to the negative kx. Now, a key feature to a logistic growth function is that we have horizontal asymptotes at y equals 0 and at y equals c. So the graph of a logistic function is going to kind of have two asymptotes to it. Now, a logistic function is, you're like, why do we care about this, right? Like, how would this be useful? Super useful, actually. For example, if you're trying to create a model to describe a population, say a population of organisms, most populations follow logistic curves because as your population increases, the rate in which you grow, your population grows, eventually levels off because after your population gets really big, you run out of resources. There's not enough food. There's not enough space. There's not enough habitat. And your population starts to level off because you've just reached the carrying capacity for your environment. If you tip past the carrying capacity, like a bunch of organisms migrate in and all of a sudden you're above, typically the population dies back out until you get to that carrying capacity again. So it's actually a super useful type of function because it describes a lot of real world behaviors, because a lot of things grow real fast and then level out. Those of you that are in the gym, your workout gains in the beginning happen real fast and then they level off, and it's much harder to get better the better you get, right? Like the hardest jump is to go from being good at something to being great at something. That takes the most work. Going from okay to good is much simpler. All right, let's look at a couple of examples. So let's say that we have the following two logistic functions. Let's find the asymptotes and then the y-intercepts. So what are the y-intercepts for A? It's always y equals 0. And the other one is y equals c. What's the c in this function? It's just the numerator. So those are your two asymptotes. Everybody feel good there? Our y-intercept. When I write the point for a y-intercept, what is the x-coordinate always? 0, right? Because it's on the y-axis. So you've gone 0 over. And the y-coordinate will just be when I plug 0 in, right? So f of 0 is going to be 10 over 1 plus 3 times 0.06 to the 0. What's 0.06 to the 0? 1. What's 3 times 1? What's 1 plus 3? So this is 10 over 4, or reduces down to 5 over 2. So my y-intercept is 0, 5 over 2. Everybody feel good there? I'm not going to bother with example B because it's like the same thing. One more example, and then I think we're on to the next section. So here it says the population of a city can be modeled using the logistic growth function, yada, 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 where P is the population in the city T years after 1950. Notice at the beginning of what year will the city have 1 million people? So I know that it says it's beginning, I'm rounding up regardless of the decimal. So to do this, all we really want to do is we want to solve P of T equal to 1 million. Everybody good there? To do that, I'm not doing it algebraically. I'm graphing it on my calculator, just like we did before. Because, Mr. Kulak, I don't know how to algebraically solve that thing. That's okay. So in Y1, I'm going to put in the logistic function I was given. In Y2, I'm still going to type in the 1 million. I'm going to set my window. 0 is 1950. I don't know how long this is going to take. So I don't know. I'm just going to pick like 100 because it could be a long time. I'm just guessing. I can always go and make that number bigger if I need to. The Y minimum, well, that's got to be 0. Because that's the horizontal asymptote. And the Y max is going to be the other horizontal asymptote, which is C. That's too annoying of a number for me to write. I'm just going to do 1.5 million. Everybody okay? And I'm going to hit graph. See what I get. So here's my logistic curve being drawn in. There's the line for 1 million. I just want to find that intersection. Second trace, intersect, enter, enter, enter. I get 79.0002. So I know I have to round that to 80. And if I want the year, or T is years since 1950. So my answer should be 2030. Everybody feel good? Okay. In section 15.2, we're going to just be talking about exponential and logistic modeling. So basically what we're going to see here is you're going to get some formulas, and we're just going to practice filling in the formulas from a story problem. So there's no new ideas here. It's just going to be like a formula, some vocab, and an example. A formula, some vocab, and example. So the first example we're going to look at is the exponential population model. So we had the logistic population example from the previous one. You can also do population exponentially. It's not as good over the long term. So in our exponential population model, P of T is the population at time t. P naught is the initial population. R is the rate of change as a percentage. And then T is some unit of time. So if I look at example 7, we're given a couple of exponential population models, and we're asked to decide whether they're growth or decay, and then find the constant rate of growth or decay. That is the R value that would be here. So I can tell whether they're going to be growth or decay just by looking at the B value. Since the first one is B is greater than 1, I know this is growth. And for the second one, because B is between 0 and 1, I know it's decay. Everybody's okay there? I did nothing other than remembered the definition of growth and decay to do that. Now to solve for R, I know that this thing is like my B because that's where the exponent is. And this is like my B. So I can take those two B's and set them equal to each other. And now I'm just going to solve for R. So I subtract 1 from both sides. And then multiply both sides by 100. And I'm done. Is that okay? Is there going to be any difference for part B? You're going to get a negative number for R, but like, whoop-de-doo-doo, it's the exact same idea. I'm going to skip doing that. Everybody okay? All right. Example, it says, determine the population model with an initial value of 15. So we're talking about an exponential population model. So I know I'm going to be using this formula. The initial value, that's the P naught. The constant rate of 6 is R. Increasing tells me that R is positive. So I'd say, okay, P of T equals P naught times 1 plus, I'm not 1, P naught is not, okay, 15 plus, or times 1 plus 6 over 100 to the T. And if I simplify that down, 6 over 100 is 0.06, and 1 plus 0.06 is 1.06. But I should say what unit T is. What unit of time should T be? Should be in years. Because I know that 6% is happening every year. So in 1 year, I get 1 6% increase. In 2 years, I'd get 2 of those 6% increases. Or that 6%, I should say that 6% increase should happen 2 times. Maybe I should phrase it probably that way. Okay. Read this problem. What's different about this one and the previous one? Yeah, the only difference is that 6% change is happening every 6 months instead of 1 year. So this is still P naught. This is still R. We still know R is positive. What's going to have to change, though? Something with our T, right? So if I say T is in years, how many times is that 6% increase going to happen in 1 year? Twice. So it should be 2T then. Everybody agree? Now, what happens if instead I wanted to make the T in months? How many times is that 6% increase going to happen in 1 month? You get 1/6 of it, right? So we'll have t over 6. Or what if I just said that? Now, this could be a hassle when actually solving, because if I get t equals 4.3, figuring out how many months that is now a big pain in the tuchus, right? I probably would lean with going with one of these two, because my answer comes out to be just years or months. So if it asks how long, that's a better answer. But usually I would pick, if I was to pick between these, it would depend on the context of the question. Like if it asked how many years, it gave me this, and then asked how many years, well, I would want to use the one with years. If it asked for how many months, I would want to use the one in months. So I'm going to be a little bit specific to the wording of the question and deciding like how I want to kind of construct that model. Does that make sense? So there's lots of correct ways to write the model, but the one you'd want to choose depends on what you want to do after you've written it. Okay. So let's do another example. It says, suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. So again, this is one of those two-step problems. We got to write the model and we got to solve the model. Everybody's okay? So in step 1, what's P naught have to be? $120. Because that's the initial amount, right? That's how much we started with. We put 120 in the petri dish and then check to see how long stuff is happening. Now, what is the R going to be? So give you R as a number. Okay, so the doubles is going to be relate to the R, but R isn't 2. R needs to be a percentage. Doubling isn't 2%, right? What percentage is doubled? What percent change is doubled? If you started at 1 and then you went to 2, how much did you gain? How many units did you gain if you started at 1 and you went to 2? You gained 1 unit. What percent of the original starting amount did you gain? 100%. What is R? 100%. Double is 100%. Now, what unit should T be in? Hours makes the most sense to me. How many doublings do we get in 1 hour? If it takes 3 hours for it to double, how much of a doubling do I get in 1 hour? Do I get more than 1 doubling or less than 1? Less than 1, right? How much less than 1? It's a third, right? If it takes 3 hours to double and we only go for an hour, we get a third of that doubling happens. So there's my model. So what I'll do then, oh, FYI, if we wanted to change, if I wanted to simplify this, that's just 2. There's the doubling, right? Because 1 plus 100 over 100 is just 2. All right, so we have 120 times 2 to the x over 3. And then that's going to be 400,000. My window, I don't know, 0 to 100 probably is okay. The max needs to be bigger than 400,000. I'll just do 500,000. I'll hit graph and see if it goes. Woo! Boy, those bacteria were going crazy. Look at how fast they got to 400,000. That was unexpected. So second trace intersect, enter, enter, enter. I get t equals 35. And because t was just in hours, that's just 35 hours. Everybody good? Am I out of time here? I hear people packing up. Okay. We'll need to finish this section then next time. But you guys should, for next problem set that's not due till next Sunday, you guys should be able to do up through 16. No, I lied. Up through 36. Sorry, up through 36.